Hello, everyone. Welcome to today's webinar. This is Sam Lee from Case Design, Sydney. Today, the weather in Sydney is quite good. The temperature is comfortable. So I wish all of you have good weather and feeling well. At the beginning of today's webinar, let me briefly introduce myself and my company. So I have been a bridge design engineer since graduated from university. In the past 15 years, I have been involved into more than 100 projects. Among them, there are 10 plus cable-stayed bridges, including some world-class projects. As you can see on this slide, I posted some screenshots of some of them. And if you are familiar with MIDAS, you will see all of them are from MIDAS. When I started my career, I tried many software in the market, including SAP 2000, LUSAS, MIDAS, and some other software. And I would say all these software are good, but to me, the most convenient one is MIDAS. So I have been using MIDAS to calculate my projects and my bridges. And my company is Case Design. We are a global company. I am based in Sydney. We focused on design and technical consulting. We do temporary work design, permanent work interface, design coordination, construction engineering. Currently, one of our major jobs is involved in Western Gate Tunnel project in Melbourne. And we provide stage analysis, we do temporary work design, and we do erection analysis, and so on. Today, my presentation is mainly consists of 3 parts. One, overview of cable-stayed bridge. The second, modeling method of cable-stayed bridge. The third, optimization of cable forces. My presentation is mainly based on my personal experience and understanding. And I chose some of them which I think is good for today's webinar. And now let's start from the first part. So I think it's good that we know a bit about the history of cable-stayed bridge. The first modern cable-stayed bridge is usually considered as Strömsund Bridge in Sweden, which has a 182-meter span, built in 1955. And the cable-stayed bridge has been developed rapidly since 1990s. Table 1.1 shows the world rank of the largest cable-stayed bridge. And as you can see, the number 1 is Rusky Island Bridge. The main span is 1,104 meters. The second, the third, the fourth bridge are all over 1,000 meters. And in Australia, the largest cable-stayed bridge is Anzac Bridge. The main span is 345 meters. Cable-stayed bridge is quite special. It has many structural features. Today, I want to mention 2 of them. One is highly indeterminate. So if we look at, generally speaking, there are 4 bridge types: arch, beam, suspension, and cable-stayed bridge. And in my opinion, cable-stayed bridge is the most difficult bridge type in terms of calculation. Because if we look at DOF or degree of freedom, we know if the structure doesn't have any redundant DOF, so it's statically determinate, it's easier to calculate by hand. But if there is a few redundant DOF, we can calculate it by hand, but that could be a headache. For arch and beam bridge, normally the redundant DOF is less than 10. And suspension bridge, someone may say suspension bridge is larger than cable steel bridge, and it looks quite, there are many redundant DOF. Yes, that's true, but actually suspension bridge is not so difficult to calculate because we can make some assumption, so we can calculate the main cable. For example, we know the Great Bridge, Golden Gate Bridge in America. So it has a span of 1,280 meters, but it was built 100 years ago. We know in that year we didn't have any software, any computer, but the people still can build such a big suspension bridge. For cable steel bridge, usually the redundant DOF number related to the number of cables. And as I mentioned before, cable steel bridge developed rapidly since 1990s. I think one reason is the development of FEM software, because nowadays we have powerful software such as MIDAS, so we can analyze highly indeterminate structure. Figure 1.2 shows the early cable steel bridge and the recent cable steel bridge. The left picture is the early cable steel bridge. We can see there are only a few cables. That's because in that year, people could not calculate very highly indeterminate structure. So they couldn't add too many cables. However, now the redundant DOF is not an issue, so we can add many cables. And increase the cable numbers is very good for structure. I will explain it further later. Another feature, structure feature is activeness. Active is the opposite to passive. For some passive structure, such as beam bridge, we know once the node P is fixed, is determined, the beam forces will be fixed. So we cannot change the beam forces. We can only accept the beam forces. What we will do is we will choose beam size, and we work out how much reinforcement and the pre-stress is required for these beam forces. But for active structures such as cable steel bridge, even node P is fixed, still we can change the beam forces by adjusting cable forces. So we are active. The beam forces will be under control of our designer. Now let's move to the second part, modeling method of each component of bridge, cable steel bridge. Normally, a cable steel bridge is mainly consisted of 5 parts: foundation, pylon, pier, girder, and a cable. So for the foundation, the most popular foundation is pile foundation. That's because the pylons are high rise to ensure the stability on the natural node such as wind node or earthquake node. So we need the structure embedded into the soil. The pylon and pier is mainly made of reinforcement concrete, but some bridges also can use pre-stressed concrete or steel. The girder can be made of pre-stressed concrete, steel, or composite. If the main span is within 400 meters, so the first choice could be the pre-stressed concrete because it's usually cheaper and durable. But if the main span is larger than 600 meters. So because the PC girder is too heavy, we need to increase the cable area, the pylon, and the foundation. It's not economy. So the first choice normally is steel. Between 400 and 600 meters, so we can use steel, and we can also use composite girder. The cables usually we use parallel wire strands or PWS. Now I'm going to show you the model method of each component. So for the pile foundation, the pile itself is easy to model because we can use beam element to model piles. But the pile is surrounded by soil, and the soil provides support to the piles. To model this kind of trend, we can consider it from two directions. In vertical direction, we can add a vertical rigid support at the bottom of the piles. For the horizontal direction, we can add a number of point springs along piles. And but we need to, another question, the question is how to calculate the stiffness of the point springs. To do this, we need to know the soil modulus and the soil area which is distributed to the point spring. For the soil modulus, when the soil is quite complicated, but one acceptable assumption is Winkler soil model. So it assumes the soil pressure is linear to the natural deformation of pile, and the elastic modulus is linear to the depth. For the soil area, we can assume the soil area is a rectangle, and the rectangle height is the point spring space, which is shown as A in figure 2.5. And for the width of the rectangle is a bit complicated. If we look at figure 2.5, we can see for a single pile, the stress zone is larger than the pile diameter. And for a pile group, because the stress zone will overlap each other, so we have some formula to consider this effect. And I don't want to spend too much time to go through this formula, and you can download this PowerPoint and you can read through it. But once we get the modulus and the soil area, we can get the spring stiffness. Some tips. The second, normally, although the total pile length may be very long, but we don't need to model all the total length because the deformation happens only on the top part of the pile. So normally 10D, and D is the pile diameter, is not enough, except in very soft soil. Second, be aware, different soil type might have different modulus. If you look at the figure 2.6, so this is an example. On the top is mud, below mud is sand, so they have different modulus. Another thing is scouring. We should ignore the soil within the scouring area. For the modeling of piers and pylon, we can use beam element to model pier, pylon, and pile cap. So for a pile cap, the area or a cross section might be very big. And some beginners may be curious about the connection between them. So I'm going to show the connection between them using figure 2.9. This is an H-shaped pylon. So there are 2 pylon columns. Each column has 1 pile cap, and the 2 circular cap are connected by a tile beam. Below pile cap, there are many piles. If we look at figure 2.10, so the left picture is the shaded view. The right pictures are nodes and elements. We can see the vertical beam represents the pile cap. The inclined beam is pile column. For some reason, the center of the pile column is not aligned to the center of a pile cap. So there is an offset. And we need to use a rigid link to connect the top of the pile cap to the bottom of a pile column. Look at the figure 2.11. So we need to use 2 rigid links to connect both ends of pile cap to tile beam. And for the connection between pile cap and the piles, we need to use rigid links to connect the top of the piles to the bottom of the pile cap. For the modeling of girder, so there are many ways to model girders. We can use a single girder. We can also use greenage, shell elements, or even solid elements. But I think that the easiest way and also the most popular way is fishbone model. Look at figure 2.13. So in the middle, it's the spine. And along the spine, there are many pairs of ribs. So in fishbone model, we create beam elements in the middle of girder. So it's a spine. And the ribs are rigid links between cables and the girder. Figure 2.15 shows an example of fishbone model. The left is the shaded view, the right is the nodes and the elements. For the modeling of cables, so we need to understand a bit about the sag effect. We know cables provide support to the girder, and it's related to the angle between cable and the girder. The cable actually, in reality, the cable is not straight because on the self weight, it will sag a bit. Once it sags, the angle will reduce a bit, so the support will be reduced accordingly. So for large span bridge, the sag effect may increase the girder displacement and forces by 10%. In the past, it was a bit time consuming to calculate this sag effect because we need to use the formula to modify the elastic modulus of cables. But now, because MIDAS have cable element type, so we can simply use cable element to model cables. The program can calculate the sag effect automatically. Now let's move to the third part, optimization of cable forces. So cable forces are very important to cable stay bridge because they determine the structural state. Look at the figure 3.1 and 3.2. There are girder bending moment diagrams of the same bridge. The only difference is the cable forces. We can see in figure 3.1, the girder bending moment is very huge. And to resist this such a huge bending moment, we need to use a lot of material on girder. That's a lot of cost. However, by adjusting cable forces, the bending moment can be reduced dramatically. It can be reduced to figure 3.2. We can see the bending moment is much smaller. And so we can save a lot of money. And in my opinion, the optimization of cable forces may be the most important and also the most difficult part during designing a cable steel bridge. To do this, firstly, we need to be clear about the criteria. In other words, by these criteria, we can compare and determine which group of cable forces is the best. So in my opinion, there are mainly 4 criteria. I will talk on them one by one. The first criteria is about the bearing. So no bearing uplift or tension is allowed. That's because common bearings are not designed for tension. Look at the figure 3.4. This is a common configuration of port bearing. So if it is in tension, it may be split and broken. Although I know in the market there are some special bearing which can be in tension, but to me, I'm not confident about reliability and durability because the bearing usually are designed for design life of 50 years. So because it's not convenient to replace the bearing after the bridge is completed. Another reason is the uplift might increase the complexity. Look at the figure 3.3. This girder sits on 4 bearings. If one of them is uplift, so the girder will become sitting on 3 bearings. And so the structural system change. We need to modify the model. And we know when design, we need to consider all the possible load combination. Sometimes if we apply vehicle load first, then we apply the wind load or the thermal load. And then in another case, we apply the wind load first and then thermal or vehicle. So that means the structural system might change a lot. And this is very complicated. So for all bridge I designed, I made all bearings in compression. If we found some bearings in tension or uplift, we can reduce cable forces near the bearing, so that will let more self-weight go into the bearing, or we can add a counterweight. The second criteria is about a girder bending moment. We want the girder bending moment as small as possible. To make it simple, we can say the girder bending moment is the combination of global bending and local bending. Figure 3.5 show an example of global and local bending. And the green line is the global bending, the red line is the local bending. Global bending happens like a continuous girder of the bridge span. So it sits on bearing, and the vertical component of the cable force counteract the girder self-weight. The local bending happens between cables. So it's like a multiple span continuous girder, and the span is the cable space. And obviously, adjusting cable forces can change the global bending, but it cannot change the local bending. However, the local bending moment usually is very small because the cable space is very small. Yeah, that's why recently compared to early cable steel bridge, the recent cable steel bridge has more and more cables. And if we find some large bending moment, the main principle is we can tension the cables a bit more to reduce positive bending moment. And we can release the cable a bit to reduce negative bending moment. The third criteria is about pinion deformation. So to my understanding, I would like to keep the pinion vertical on the cohesive permanent node combination. We know cohesive permanent node combination include permanent node and also live node such as vehicle node. And typically, vehicle node will make the pinion incline towards middle span more than to the side span. That's because middle span is larger than end span. So to counteract this deformation, we need to make the pinion a bit inclined to end span when it is completed. And to achieve this, we can tension the cables on end span. The fourth criteria is about the cable force. Cable forces should vary evenly from near to further away from pinion. So we can see the vertical component of cable forces counteract the girder self-weight. And if the girder self-weight is evenly distributed, so the vertical component of cable forces should be similar. So the cable forces will be determined by the angle between cable and girder. Because the angle change gradually from near to further away from pinion. So the cable force should also change gradually. And but at some point, such as anchor pier or the closest cable to the pinion might be an exception. If we find some cable force too large or too small, we can adjust them, but be aware the cable forces can interact each other. That means when you change one cable, the other cable force might be affected. It's important we also understand a bit about the construction method of cable steel bridge because it has large influence on our calculation. So for large span cable steel bridge, the most popular method is balanced cantilever method. Figure 3.9 shows one application of balanced cantilever method. So typically for each segment, there are many 3 steps. The first step, we erect girders symmetrically or balanced. So that means erect the left segment and the right segment at the same time. The second step is we install and tension cables on that segment. The third step is we move current forwards, and then we repeat these 3 steps for the next segment again and again. I would recommend you to always consider construction stage during modeling. And however, if the calculation is only for concept or preliminary, so we can only use one stage for each segment. And if it is for detail and construction, so we need more stages, such as 3 or 4 stages for each segment. Of course, if you only require a rough calculation, it might be acceptable. You not consider stage analysis. For the optimization method, and actually, this is a well-studied topic, and if you search online, you will find lots of paper on it and dozens of optimization methods. And today I want to mention two of them. One is stiff cable method, another is unit node method. The first method is quite simple and easy, but the result is not perfect. The second method is more accurate, but it's a bit time-consuming because it requires iterations. However, one good thing is MIDAS has some built-in tools, and which can help us to save considerable time. I also want to mention during the optimization, our observation is very important. We need to look at the result. We need to think about how to change the force next step. So for the first optimization stiff cable method, so we know the cable is supported on the girder is supported on cables. Imagine if the cables are very soft. In extreme cases, the cables are as soft as noodles. So we know noodles cannot provide any support to the girder. So we can ignore cables. The cable stability will not be a cable stability, it will be a continuous girder bridge. On the contrary, if the cables are very stiff, so the girder will have the minimal deformation and the beam force as well. So at this moment, the cable forces are best for a girder. To do this, we can follow 5 steps. First, we create a model as normal analysis, but we don't need to input any cable forces. Secondly, we increase cable stiffness. So to do this, we can either increase the cable area or increase the modulus. I think it's easier to change the elastic modulus because it's only one number. Then we run the analysis and we extract cable forces at the last construction stage. But now it has not been finished because we also need to observe the result. Sometimes there might be negative cable force or excessive cable force. In that case, we need to adjust manually. Look at figure 3.10. So we can see the blue means compression. But usually near the blue, near the compression force, there are very large cable forces. So we need to average them by hand. The second method is a unit node method. So to help you better understand the unit node method, I want to compare it with metric stiffness method in structural mechanics. Because I suppose most of you have learned this course in your university. And we know the metric stiffness method can be expressed as figure 3.11. So N is the number of DOF, vector F is the nodal force, vector theta is nodal deformation, and the metric K is stiffness matrix. Kij is the Fi caused by 1 unit of theta j. So the vector F and the metric K are what we have learned. We can work out this. We can work out the data by solving this matrix algebra. The unit node method can be expressed as a similar equation, but N is the number of cable retention forces. Vector F is the constraints. Vector data is the cable force factors. Matrix K is the influence matrix. Kij is the Fi caused by 1 unit cable force of data J. We can understand this method by 2 examples. So example 1 is a simple cable state structure. If we say 1 kilonewton cable force causes 10 mil deflection at beam end, then how much cable force is required to make deflection 20 mil? So in this example, the matrix K is 10 because 1 kilonewton cable force causes 10 mil deflection. And the constraint vector F is 20 because we want the deflection is 20 mil. So we work out F equals K times data. We can get data is 2. Example 2 is a bit more complicated because there are 2 cables, cable 1 and cable 2. If now we know 1 kilonewton in C1 causes 10 mil deflection at node 1 and 15 mil at node 2. 1 kilonewton in cable 2 causes 15 mil deflection at node 1 and 25 at node 2. So from these 2 sentences, we can work out the influence matrix. Then we ask how much cable force is required to make the deflection at N1 40 mil and at N2 65 mil. From this sentence, we can know the constraint vector F. Then we work out the equation, and we can get the data vector. For the dimension of a vector and a matrix N, so actually the N equals to the number of cable retention forces. So it's not the same to the number of cables. For example, figure 3.13 and 3.14 are the elevation and cross-section of a cable steel bridge. On the elevation, we can see there are 20 cables, and on the cross-section, there are 2 cables. So totally there are 40 cables. However, on the elevation, it's symmetric. The left part is mirror to the right part, and the left part has the same force to the right part. In other words, for example, the left S3 cable will have the same force to the right S3 cable. And on the cross section, the 2 cables will share the same force because otherwise it will cause some torsion or transverse bending. So for this bridge, actually there are only 10 cable forces, so the N will be 10. For vector F can be a certain number, or it can be a range. In theory, it can be any force deformation reaction at any point, but normally F is set to be bending moment or deflection of girder or pinion or whatever. Vector data, so it's the factor of unit node. Please notice 1 unit node can be any value. So if we take the example 1, for example, if we set 1 kilonewton as 1 unit, so the matrix K is 10, and the data will be 2. But for some reason, if we set 2 kilonewton as 1 unit load, so the K will be 20 and the delta will be 1. For the influence matrix K, so I think this is the most important or the core of utility node method, because in my opinion, it helps improve engineers' understanding of cable force effect. We see nowadays we have a very powerful software, so it can do a lot of things. Yeah, some engineers they know how to input data into a software and then they get the data. It's good, it's quite convenient. But on the other hand, yeah, some engineers, especially some young engineers, they become relying on new software. We see they don't think too much. They just input and output and then finish their job. And it's not good for engineering, because we need to develop our concept or our understanding. So we say we don't want to be slave of software, although software is very good. And when we work out the influence matrix K, we need to go through all these cables, and then we look at the good bending moment, the deformation, the reaction, the planar, all these things, the influence. So during this process, we will deepen our understanding, and then we will know, if next time we do a design, we will know how to adjust the cable for some purpose. For example, if I find some large deformation, I want to reduce it, then I know which cable to adjust and how to adjust. And I want to show you an example. So figure 3.15 is a cable step bridge. It is constructed using the cantilever method. And now if I'm going to look at the influence of tensioning the eighth cable in the middle span. So please notice, because the left cable or left eighth cable is the same to the right eighth cable, so they share the same cable forces. Then we go to MIDAS. First, we look at the deformation. We can see. So first, we will see it will not have influence on the elements which are installed later than the eighth cable. So because it uses cantilever method, and we can see the middle span deflect upwards, and the planar looks also deform a bit, and the side span doesn't deform much. Oops. If we look at the bending moment, we can see the middle span has a larger bending moment, positive bending moment, and the maximum bending moment is about 4 cable space away from the good end. The pinons are also in bending, and the end span doesn't have much bending. Then, if we look at the cable forces, we can see the cables in the middle span will have some compression. Yeah, that's because when we tension the eighth cable, so the girder deflect upwards. So the distance between pinon and the middle span will be reduced. that will cause some compression in the cables. However, in reality, these cables will not in compression. Will not in compression. That's because the cables will have had some tension already. So although tensioning the S cable causes some compression in the other cables, but totally these cables should still in tension, but the tension force could be reduced. The last part I want to mention is about the nonlinear behavior. We say for cable steel bridge, especially for large span cable steel bridge, we cannot ignore the nonlinear behavior because it might come from geometry. It might also come from material. So the material such as concrete shrinkage, creep, and we say the unit node method is linear because the matrix is linear. But we can use a unit node method to consider nonlinear behavior by iteration. This is similar to the dependent line method. So the first step, we can assume cable forces. Then we run analysis. The second step, we will get influence matrix K, and then we work out the data using the equation F equals K times data, and then we change cable forces as data times unit node in the model, and we run analysis. We say whether F is within tolerance. If it's within tolerance, we quit iteration. Otherwise, we just repeat. So generally speaking, we use many iterations, and for each iteration, we check whether it's within tolerance. If it's not within tolerance, we will modify the matrix K, and we start analysis again. So today we talked about the history of cable steel bridge. We talked about the structural feature. We discussed about how to model each component of a cable steel bridge, and we also looked at the optimization criteria and the two optimization method. Yeah, that's my presentation today. Yeah, thank you.